time. Okay, so here's the setup for this problem. Exponential growth occurs when or here's more of the description, something not the setup for a problem yet. Exponential growth occurs when the population grows at a rate proportional to its current size. That's actually a pretty important thing to know because you're definitely going to revisit exponential growth and how it kind of works as a differential equation when you take one of the various, like, it occurs in different like A's or B's or C's depending on which calculus series you're taking. But just about every calculus series at some point talks about how exponential growth and exponential decay come from a differential equation where the rate of growth is proportional to population size. Population size is maybe not the best word to use there. Because it can really be with the rate of growth of a thing is proportional to how much thing you have. So that can be like human population, right? The more humans there are, the faster the rate of growth of the number of humans, right? If you have 10 humans, you're not going to get a larger growth. If you have 1 million humans, you're going to have a lot more humans per year. Or bacteria, the more there are, the faster they grow. Or radioactive substances, right? Those actually decay exponentially. So if you have a certain amount, you lose a proportion of that. But then, right, so like if you have 100 grams, it takes 20 years to lose 50 grams, but then it takes 20 years to lose 25 grams. So the rate of growth or the rate of decay actually slows down. Atmospheric pressure is an increase in elevation. That one's always, that's more of a chemistry example. And then of course, interest, right? We talked about interest last class, right? The more money you have, the faster your money grows. It's not growing at the same rate every year if you're compounding interest continuously. It's growing more and more each year, each time you compound interest. So here's the model for exponential growth or decay. And it is the same as the model for compounding interest continuously. It's given this way. Y of t equals c e to the k times t, where y of t is the amount of stuff at time t. So that could be the amount of money, like A of t was when we talked about what's after proportion, sorry, is proportional to population size. Sorry about that. So yeah, so y of t is the amount of stuff you have at time t. It could be money, it could be people, it could be bacteria, it could be radioactive substance, right? It's just whatever you're talking about you having, it is how much of it you have. And then C here, that's your initial amount of stuff. At time 0. Just like when we were talking about the compounding interest continuously, that C, we use the letter P instead, and that's the principal or the initial amount of money you have at the beginning with time 0. E is the number, right, about 2.7. T is the number of years. Well, I really should say it's not, it's really the amount of time. And it kind of depends on how you measure things, right? If you're talking about interest, then yes, T is the amount of time measured in years. But for bacteria or other things, sometimes we use a different measure of time. So it could be time in seconds, or minutes, or hours, or weeks, or days, or whatever. Like it'll be usually spelled out very clearly what unit of time you're using. And lastly, K is the relative growth rate. It's kind of like the interest rate, but not exactly. So, yeah. Right. So I should actually say, K is the rate of the population, or the whatever you have is growing relative to how big the population is. All right. Don't worry too much about knowing how K, like what the words are for K. So let's talk about an example here. I need to to my other screen. One sec. So consider a medical researcher studying a newly discovered species of bacteria. Here's what we know. We know that at time 0, there are 100 bacteria. And then later, actually we don't, sorry, not later. We know its growth is modeled by, we use the word modeled a lot, right? The equation y equals c to the kt is the model for exponential growth of decay. So its growth is modeled by y equal to, y t, I should really say, equal to 100 e to the 0.25 times t. And so we can see that as time goes on, the amount we're increasing by each hour, sorry, time is in hours, the amount we increase by each hour is going to increase, right? The rate of growth is getting bigger and bigger and bigger. So let's see how many bacteria. I like to make a table often when I'm dealing with these exponential growth and decay problems. It kind of helps me remember what's what. So I usually put time in my left-hand column and the amount of stuff y is in my right-hand column. So time equals 0. I'm just going to plug in 0. I'm going to 100 times e to the 0.25 times 0. 0.25 times 0 is 0. E to the 0 is 1. So this is just 100 times 1, which is 100. Not surprising, right? We are told that at time 0 we had 100 bacteria. So then, how about an hour later? Well, an hour later, we're just going to substitute in t equal to 1. So we're going to get 100 times e to the 0.25 times 1. That's 100 times e to the 0.25. I need the calculator for that. That's approximately 128. So in the first hour, we had an increase by 28 bacteria, right? So the rate of growth that first hour was 28 bacteria per hour. That's how fast we grew. But then in the second hour, at the end of the second hour, we're going to have 100 times e to the 0.25 times 2, which is approximately 165. So from hour 0 to hour 1, we grew by 28 bacteria. From hour 1 to hour 2, we grew by 47 bacteria. So in that first hour, the rate of growth is 28 bacteria per hour. In the second hour, the rate of growth is 47 bacteria per hour. So you can see, right, that the rate of growth every hour is going to be larger because the rate of growth is proportional to the population size. The bigger the population, the bigger the rate of growth. That's the whole point in this example, just to see that, oh yeah, as you have more population, you have a higher, faster rate of growth. We go to the third hour, 100 e to the 0.25 times 3 is approximately 212 bacteria, which means in that third hour, we grew an average of, sorry, I made a small mistake in my previous number here. 165 minus 128 is 37. Sorry about that. Small error. The reason I noticed that is because the next difference is actually 47. So from hour 1 to 2, we grew at 37 bacteria per hour. From hour 2 to 3, we grew at 47 bacteria per hour. How many will we have after one whole day? So when time is 24 hours, the amount of bacteria would be 100 times e to the 0.25 times 24. 0.25 times 24 is a quarter of 24, which is 6. So that's 100 times e to the 6th power, which is approximately a lot, 40,403. So another really important aspect of exponential growth and decay is that things get big really fast. If you have something that is exponentially growing, your numbers are going to get really, really, really large. That's so. In case you can't see what I've written because my writing is not great today, and it's 40,403 approximately. All right. So let's look at some examples. And a lot of these examples are going to be very similar to solving the compound interest formulas in your previous homework. So look at the following example. So here's the setup. Colony of bacteria. So we get bacteria. Colony bacteria is growing exponentially. And then this problem specifies that it's in a petri dish. Initially, so at the beginning, there are 40 bacteria. And then 2 hours later, there are some other number, 120. Our job, the first, so there are 2 questions, maybe there's actually 3 questions in here. But the first question, and this is really, so I could not write the first part and we still have to do it. The first real question is, how many bacteria will there be in 5 hours? Before we can answer that question though, we need the model. So the first question, even if it's not asked, is find a model for the growth. Meaning, the model is always this, y equals c e to the kt. People use other letters sometimes, people like a e to the kt or a e to the rt. Doesn't matter what letters you use for the constants. And our job is to figure out what the constants C and K. That's what we have to do before we can answer any questions. So the way we're going to do that is by using the 2 pieces of information that we get. We almost always need 2 pieces of information about how much stuff there is at a certain time. And that's why I like to facilitate it. So I know at the beginning, at time 0, there are 40 bacteria. So when time is 0, y is 40. Right? Y is the number of bacteria. And t is the time in hours. I also know that after 2 hours, the amount of bacteria is 120. I could actually use this information to say more, right? I can see that every 2 hours, this population is going to triple. So although I don't need this, you could say time equals 4 hours, the population would be 360. And another 2 hours later, it would be triple again. That is something that is true about exponential growth and decay, that the amount of time it takes to multiply by a certain number is always the same. So the amount of time to triple or double or quadruple is always some set amount. Here, it happens to be, we can see it triples in 2 hours. But again, that's not always super helpful. So first I'm going to plug in t equals 0. Now, you can kind of cut this stuff out if you want. I'm still going to show it here. If I plug in this information, I'm going to get, so let's see, so y is 40. And t is 0. And then k times 0 is 0. E to the 0 is 1. So I end up getting 40 equal to c times 1, or just c equals 40. I don't think you really need to do this step. If you know that at time 0 you have a certain amount, that amount is your c. This constant c here is often called the initial value. Some people call it C naught, if you like. So now we can refine. We know that our model is y equals to 40 e to the kt. And now we're going to plug in the other piece of information to figure out what k is. So I'm going to plug that in. I'm going to need to use the other side of the board, but I'm going to have, so when I plug this in, y is 120. And k is 2. So I'm going to solve that equation. 120 equals 40 e to the k times 2. So whenever I'm trying to solve for something that's in an exponent, I always need to get rid of any coefficient multiplying out. So divide both sides by 40. 120 divided by 40 equals e to the, I usually like to write that as 2k, although it doesn't really matter what we're multiplying. 120 divided by 40 is 3. So 3 equals e to 2k. Take the natural log of both sides. Natural log of 3 equals the natural log of e to the 2k, which is just 2k. So the natural log of 3 equals 2k, and k equals the natural log of 3 all divided by 2. So that means our model is y equal to c, which is 40, e to the k, which is natural log of 3 divided by 2, times t. That is our model for exponential growth of this particular vectorial column. So then we can plug in any other time to answer questions that might be asked. So question B on this particular problem is, how many bacteria will there be in 5 hours? And to answer that question, we just set t equal to 5. Often I like to keep my little chart going, or if I have time and amount. So now I'm asking, how many are there when time is equal to 5 hours? So I'm going to plug in 5 for t. So I get y equal to 40 e to the natural log of 3 over 2 times 5. And really, there's not much more we can do without a calculator. So I would kind of leave it like this, unless I had a calculator. If I had a calculator, I would use it, and I would get approximately 624. Which seems reasonable, right? We know that after another 2 hours, it should triple again to get to 360. So then after another hour for that, it definitely seems like 624 seems not out of the question. I don't know. The other, so I should also point out, once you have taught, I'm not sure what your question is, Jonathan. When do we plug in 40, maybe? We plugged in 40 in the very beginning. Why did we plug in 40? So back in the beginning, right, we plugged in, right, because so we knew that initially there were 40 bacteria at time 0. So when we plugged in time equal to 0 and 40 equal to y, we got 40 equal to c e to the k times 0. And that allowed us to solve for c. We're not plugging in 40 over here, right? So we're using the fact that in our model, c actually is 40. Right? It's not so much that we're plugging it in, it's that that is the value that c is. So I plugged in 5 for t, and I got 40 e to the natural log of 3 over 2 times 5, which is approximately 624. And then the other question, question C, is how long does it take for the population to double? So if I started with 40 bacteria, I'm asking how long it takes to get to 80. I'm asking for the time. 2 things about this. Thing 1, if they're asking how long it takes to double or triple, you're talking about doubling or tripling or multiplying by whatever factor of the initial amount. So if I said, how long does it take for this population to quadruple, you would say, oh, I want to quadruple the initial amount of 40. So I'm asking how long it takes to get to 160. We're always comparing to the initial timing, 0 amount. The other thing that I want to mention is, once we have the model, there's only really 2 kinds of questions we can ask. I can ask you, when it's this time, how much stuff do I have? Or when we have this much stuff, what time is it? Those are the only things I can really ask, either what time is it or how much stuff do I have. So in this question, I'm saying I have this much stuff. I want to know what time it is. So in my model, y equals c e to the kt, I'm setting y equal to 80, and I'm trying to solve for time. And just like when we were solving for k, right, we're trying to solve for this thing that's in the exponent here. So we're going to do the same. Really, this is very similar to when we solve for k. I'm going to divide by 40. 80 divided by 40 is 2. I have e to the natural log of 3 over 2 times t. And I take the natural log of both sides. So the natural log of 2 equals, so the natural log of e to the stuff, right? Just like over here, the natural log of e to 2k was just 2k. Here, the natural log of e to the natural log of 3 over 2 times t is just the natural log of 3 over 2 times t. Right? The natural log of e to a thing is just the thing. Then we solve for t by multiplying both sides by 2 and dividing both sides by 3. And that ends up being, with the calculator, approximately, if I write it down here, approximately 1.26 hours. Again, which makes sense, because we know it takes 2 hours to get to 120, so it should take less than 2 hours to get to 80, which is double what we started with. Questions? Okay. Most examples kind of go this way, where we're told something grows or decays exponentially. We start with the model, y equals c e to the kt. We solve for c, we solve for k, and then we use that model to answer some other question. So let's look at this next example. Radioactive waste. So if someone says the word radioactive, so I'm not even thinking, we're talking exponential decay here, meaning the amount of stuff we're going to have is going to be smaller as time goes on. So radioactive waste is dumped in the middle of the desert and left to decay. So radioactive. And here's what we have. A 12-gram sample decays to 10 grams in 25 days. And the question is, how long until half of the original amount remains? Also known as the half-life. Okay, so I imagine many of you, probably most of you, have heard of how a half-life is. Just if you haven't, a half-life is exactly what we've written here. It's how long it takes until there's only half of what you started with left. Oh no, I'm so sorry to hear that. Thank you for letting me know, Sophia. I had that same problem this morning. My power went out for 5 minutes or for 5 seconds, but I definitely, not that I was in a Zoom meeting, but my computer was out. So I hope she's able to join us. The last word says remain. So it says how long until half of the original amount remains, which is the half-life. Okay. And that's a typical, so typically like when someone says like the half-life of carbon-14 is, I think it's like 5,000-ish years, it means it takes 5,000 years for only half of it to be left. And it takes another 5,000 years for only half of that to be left, and so on and so on and so on. So again, radioactive decay, exponential decay, we're starting with the model. And the model, of course, is y equals CE to the kT. You will definitely see some textbooks, especially if you take, I think, the 17 series, they often, instead of writing as y equals CE to the kT, they write it as y equal to lowercase m sub 0 e to the kT. M is supposed to stand for mass, the amount of stuff we have. It doesn't matter. It's just a constant. You can call it whatever you like. I usually use C, but I'll use M not here just to be different. And then I'm going to make my table. My table says, okay, I have my time, I have my amount. I know at time 0, I have 12 grams. I know 25 days later, I have 10 grams. I'm also asking the question, how many days until there's half of what I started with, which is 6 grams. So we're going to use these two pieces of information to figure out what that was. But first, to figure out the model. All right, let me ask you guys. Instead of plugging in time equals 0, what do I know m naught's going to be? I'm going to write y equals what times e to the kT. Yeah, exactly. It's definitely 12. It's always going to be that constant. There's always going to be the amount to start with. If you're not given an amount, sometimes it's a little more work. But yes, if you know that at the beginning time you have a certain amount, that just goes. But you can also plug in 12 here and 0 here, and then solve and get the m naught constant, or the c constant is equal to 12. So then we're going to plug in this information. So my y value is 10. My time value is 25 days. Now we're going to solve for k. So 10 divided by 12 equals e to the 25k. I can reduce this 10 divided by 12 to 5 over 6 and take the natural log of both sides. So I've got 5 over 6 equal to e to the 25k. And I can take the natural log of both sides. So then the natural log of 5, 6 on the left is equal to the natural log of e to a thing is just the thing. So I end up with k equal to the natural log of 5, 6 divided by 25. And so my model here for exponential decay, my model is y equal to 12 times e to the k, which is that natural log of 5, 6 over 25 times t. So there's my model for exponential decay. And then to answer the question, right, to figure out what time it is when half of it has decayed or half of it's left, same thing. I'm going to set the amount of stuff I have to half of what I started with. So I'm going to set y equal to 6 and then solve for t. I need the other side of the board, unfortunately. So again, here's my model, y equal to 12 e to the natural log of 5, 6 over 25 t. I'm just setting that equal to 6. So 6 equal to 12 e to the natural log of 5, 6 over 25 t. And just like every other time, we're going to solve for t the same way. We're going to divide by this coefficient. We're going to take the natural log of both sides. Then we're going to isolate t. So divide both sides by 12. 6 divided by 12 is 1/2. That shouldn't be surprising. If we're trying to find the half-life, whenever we divide by what this coefficient is, we're always going to get 1/2. This is half of that. And this divided by that is 1/2. And we take the natural log of both sides. On the left, we get the natural log of 1/2. On the right, the natural log of e to a thing is just the thing. So we're just getting this, which is the natural log of 5/6 over 25 times t. Multiply both sides by 25, divide both sides by the natural log of 5/6. So we get the t is equal to the natural, so 25 times the natural log of 1/2 divided by the natural log of 5/6, which is approximately equal to 95 days. All right. Nice little cracky there. Questions regarding any of this? This process can get a little bit tedious, right? Or not so much tedious, it's just repetitive. It's the same thing kind of over and over again with some slight variations. So, yeah, I want to look at, sorry, I got a couple more examples I want to do. One of them I think is more important than the other. So I'm going to do the last example next, and then we'll go back to the mouse example so we have time. So the last example on the notes, on the blank notes, we're going to find the half-life of a radioactive material if after 3 years, 20% has decayed. So I want to know the half-life. What I know is it's radioactive, and after 3 years, 20% has decayed. And this is actually meant to be, this is kind of meant to trick you. I mean, I don't really want to trick you, but I want you to be aware of how someone might try. So the thing to remember about any of these equations, whether it's radioactive decay, whether it's population, whether it's bacteria, is that the equation is always about how much stuff you have, not how much stuff you don't have. So when I start making my little table here of time and the amount of stuff I have at t, that's the other problem here. No one told me how much I started with, right? They just told me that later on I have 20% less. This is actually the nicest situation possible. So if no one tells you how much you start with, pick whatever number is convenient. And this is the number I'm always going to pick. I'm always going to pick to start with 100. 100 grams or 100% or 100 kilograms or 100 pounds, whatever thing you want to think of having 100 of, that's fine. Because then if I have 100 grams to start off with, I know that 3 years later, how much do I have? I'll give you a hint. It's not 20. It's 80, right? I lost 20%. But the equation is all about how much I have. So if I lost 20%, I still have 80% of 100, which is 80. So that's how I would set up this problem, right? I would definitely, if they didn't tell me how much stuff there was to start with, I would say, okay, I'm going to start with 100. And if they're telling me how it's decayed by 20%, well, if I lose 20%, I still have the other 80%. So that's how much I have for 3 years. All right. Let's write, and then the equation is, and oftentimes the question is, or not the equation, the question is what's the half-life? So the question is, what time is it when I get to half of what I started with, which is 50%, 50 grams, 50 kilograms, whatever units you're thinking of. All right, so usual model, y equals c e to the kT. And we already know that that c there should be 100 because that's what we decided our initial amount is. So y equals 100 e to the kt. Then we're going to plug in this piece of information to figure out what the k constant is. So I'm going to plug in 80 for y, 3 for t. So we get 80 equal to 100 e to the k times 3. And then I'm going to solve for k. 80 divided by 100 equals e to the 3k. 80 divided by 100 is just 0.8, which is literally just 80% as a decimal. And that should happen, right? If they're saying you have 80% after 3 years, which is what they're saying here, it means when you divide both sides by that constant, you'll get 80% on the other side. So then we take the natural log of both sides. Natural log of 0.8 equals the natural log of e to the 3k is just 3k. Finally, divide both sides by 3, you get k equal to the natural log of 0.8 divided by 3. So now our model looks like y equals 100 e to the k, which is natural log of 0.8 divided by 3 times t. And now we're going to plug in 50 for y to find out what the time is, or the half-life. So we're going to take that part there and say, okay, 50 equals 100 e to the natural log of 0.8 over 3 times t. It's the same thing every time. Divide both sides by that. 50 divided by 100 is 1/2 equal to e to the natural log of 0.8 over 3 times t. And then take the natural log of both sides. Natural log of 1/2 equals the natural log of e to the stuff is just the stuff. Natural log of 0.8 over 3 times t. Multiply both sides by 3. Divide both sides by natural log of 0.8. And that's your t value, which is approximately, you know what, I don't think I actually have this one worked out ahead of time. So, I guess I could do it on my calculator. I can use a calculator. So on a calculator, that's going to be, let's see. So natural log of 0.5 times 3 divided by natural log of 0.8 is about 9.3 years. Interesting. Okay. Yeah, that makes sense. So another way you could say this, although it's kind of weird to say it this way, is that this is going to decay by 20% every 3 years, right? Once you know how long it takes to decay by a certain percent, that's always true. So after another 3 years, so when I got to like year 6, I would have lost another 20% or had retained 80%. And 80% of 80 is 64%. And then after another 3 years, I would lose 20% of 64%, or I'd have 80% of 64%, which is about 51.2%. So it makes sense, right? If I lose 20% every 3 years, after 9 years, I'll have lost almost all the way down to 50%, right? 100% goes down to 80%. 80% of 80% goes down to 64%. 80% of 64% is 51.2%. So after 3, 6, 9 years, we're at 51.2% of where we started, which seems pretty reasonable then that the half-life is 9.3 years. That's kind of nice. I like that. All right. We've got enough time, so we definitely should do the last example. So the last example says 2 months. Oh, this one's kind of meant to be a little bit challenging because they're saying they're messing with the time frame here. So 2 months ago, 2 months, wow, months ago, we had 3 mice. Now we have 18 mice. What will the population be in 2 more months? So here's how I would set this up. So even though 2 months ago is right, it's kind of like that's when you're, how do I want to say this? So people often set this up kind of the wrong way. I feel like the wrong way is to do it this way. Although it's not wrong, it just is less easy. If you set now is time 0 and you say we have 18 mice, and then 2 months ago is negative time, and we have 3 mice, I find that confusing. So what I prefer to do is to say, okay, 2 months ago, that's time 0. And then 2 months later, so time has moved forward 2 months, we have 18 mice. And then 2 months more later, we're wondering how many mice we have. This one you could totally answer without doing any of the stuff we've done before. Because we can see that in 2 months, the population is multiplied by 6. So in another 2 months, the population should also multiply by 6. So we should get to 108 mice. And that is actually what we get to. There's a couple ways to do this. How much time do I have? Not a lot of time. So, yeah. So using this first information, we have y equals 3e to the k times t, right? Time equals 0, y equals 3. I plug it in, I get 3 there. Plugging this information, y is 18. It's equal to 3e to the k times 2. Divide by 3, we get our 6. That's equal to e to the k times 2. Take the natural log of those sides. So that k equals the natural log of 6 over 2. So I can write my equation as, now actually I want to show you guys something because this comes up a lot, especially in the 17 series. So I could write it as y equals 3e to the natural log of 6 over 2 times t. But here, especially in this example, you might rewrite, so, and then I should say, you could plug in 4, and when you plug in 4, you'll totally get 108. You could also rewrite this as 3e to the natural log of 6 to the t over 2 power, right? When you write a power to a power, you would multiply the powers. So this power would be natural log of 6 times t over 2, which is exactly what we have here. But then e to the natural log of 6 is just 6. So you can totally write this as y equal to 3 times 6 to the t over 2. So that every time t increases by 2, you multiply by 6, right? When t is 0, you get 3 times e to the 6 to the 0, which is just 3. When t is 2, you get 3 times 6 to the 1, which is 3 times 6, which is 18. And when t is 4, you get 3 times 6 to the 4 over 2. 4 over 2 is 2. 6 to the second is 6 squared, which is 36. And 36 times 3 is 108. Or you could use the other model and plug in t equals 4 here. And get y equals 3e to the natural log of 6 over 2 times 4. Which if you plug that into a calculator is going to be exactly 108. So either way will get you to the same answer. But sometimes I don't personally prefer to do it this second way, which is why I haven't really talked about it a whole lot. But some people really like to take this expression and rewrite it as a different number to a t over a number kind of power, which is just, it's still equivalent. It's just not exactly looking the same. All right. So the things to take away from exponential growth and decay are the following. The model is always the same. The model is always y equals c to the kt. There are other kinds of growth, like logistic growth and some other things that you'll learn later on, mostly in the 17 series, that are not modeled like this. But as far as we're concerned, our model is always this. We're always going to start with that. We're going to use our data to solve for the constants c and k. And then after we have fully fleshed out the model, so we know what the C value and the K value are, then we're going to answer whatever question is asked about either how much stuff do I have at a certain time, or what time is it when I have a certain amount of stuff. So if I say, what time is it when I have, 20%, 10% of what I started with, I'm going to plug in 10% for Y and find the time. Or I could say, how much stuff do I have when it's been 12 years? And I would plug in 12 for T and find the amount of stuff. But those are really the only kinds of questions you can ask. If I tell you what time it is, how much stuff is there? If I tell you how much stuff there is, what time is it?